What's up everyone? Welcome to TheMKLabs. Glad you're here. This is video 3 in native quality engineering. In V1, we mapped the terrain. We talked about what production AI systems actually look like and why the old testing playbook doesn't quite fit. In V2, we got into the anti-patterns, the 3 things I see in almost every engagement that quietly erode quality. Human as ceiling, looks good to me culture, snapshot equality. Now in V3 is a resolution. This is the so what do we actually do about it video. Frameworks, code, and the eval pipeline that holds up under pressure. Let's get into it. Building the layered defense. Sounds like an army situation, right? Well, let's not get into it. The world needs peace, but your AI systems, that definitely needs a different strategy. And that's exactly what we are building today. Hi, I'm Manoj. This is video 3, and this is the one that everything comes together in the past 2 years that we looked at. Now V3, no more pointing at problems. Today we build frameworks, real code, and eval pipeline that holds up under actual production pressure. The practical mechanics as it says on the screen. So grab your coffee, settle in, and let's get into it. By the end of the video, you'll have a blueprint that you can take back to your team. So quick context for anyone jumping in fresh. This is part of a founding trilogy. V1 set the scene. We used the toast notification story to show how AI systems fail differently from traditional software. V2 diagnosed the problem, 3 anti-patterns that show up everywhere and manufacture false confidence. And now V3, this one is the practical build. We are going to construct a layered defense layer by layer with real code and real frameworks you can take back to your team. If you haven't watched V1 and V2 yet, I would recommend going back and then come back to this. You will still get a lot out of this one if you're just wanting to know only about the layer difference. All right, here's exactly what you will walk away with by end of the video. 3 things. First, the 4 layers, each one with named frameworks and tools you can actually start using the next day. No hand waving, no it depends, concrete picks. Second, the cascade, how those 4 layers wire together into a single eval pipeline. Because individual checks are nice, but an integrated pipeline is where actually catches things in production. And third, we are closing the open thread from video 1, drift detection and self-heal. How do you know when the system is drifting? And what do you do about it automatically? That's the loop we left open, and today we close it. All right, Act 1, the frame. Before we dive into layers themselves, I want to show you something that should feel very familiar, because the shape what we are building, you already built it before, just with different content inside. Look at this pipeline. The linter, unit, integration, smoke test, and manual QA. Functional testers. You've trusted this shape for decades or more, right? Each layer catches what the previous one couldn't. Each layer saves the expensive layer from running on something that always going to fail. Now, here's the key insight. The same pipeline shape that works for AI. The content inside each layer is different for sure. You're not checking syntax anymore. You're checking schema conformance. You're not testing function contracts. You're testing property invariants. But the architecture, the cascade, the cheap first, expensive later logic. So if the shape already makes sense to you, and it should, then the layered defense is going to feel like home. Now let's talk money, because this is where it gets real for anyone who needs to justify this to leadership. Like layer 1, schema checks. We are talking cents per artifact. They're fast, they're cheap. Layer 2 is property check. Small ballpark cents per artifact. Still programmatic, still fast. Layer 3, model graded eval. Now we're talking dollars. Maybe serious dollars, depending upon the model and the volume. This is where you're calling another LLM to evaluate the output. You only want this running on artifacts that already survive layer 1 and layer 2. Layer 4, human sampling, the most expensive layer because it's people's time. And that's exactly why it runs on curated sampling, not on everything. The whole design principle here is cheap to expensive, deterministic to probabilistic, programmatic to judgmental. Each layer earns the right for the next layer to run. Act 2, the 4 layers. This is the core of the video. We're going to walk through each layer one by one: schema, properties, model graded eval, human sampling. For each one, I will show you what it does, why it matters, and the actual code or the framework you would use based on what I've seen in the market. Let's start at the bottom, right? Layer one, the schema checks. Think of this as a linter for your AI testing pipeline. Here's a principle. If your code doesn't compile, you don't run the test. Same thing. If your AI artifact doesn't parse, doesn't conform to the expected structure, you don't run the eval. As simple as that. You reject it immediately. This is the cheapest, fastest check in the whole pipeline, and you'd be surprised by how many failures it captures. Remember the half-emitted markdown from video one that we saw? Schema checks catch that artifact one. Not after you've spent dollars running model-graded evals on garbage. Now let's get practical and see what this looks like in a code. Again, that is something that you can build it using a Python library like Pedantic. You define the expected schema. You can have things like test ID, description with minimum length, assertions list that must have at least one item, customer ID. You can build in a timestamp. And then in your CI pipeline, you can validate the model output against the schema. The one where the model stopped generating mid-response and you caught the artifact with 0 assertions. Without this check, that broken artifact flow downstream, burns through your model-graded eval, and gets confusing low score that someone has to manually investigate. With this check, rejected instantly. That's the power of catching failures at the right layer. Layer 2, the property checks. Think of this as contract tests for your AI artifacts. Contract testing, we have done this before in the microservices world. Similar to that, 3 categories, right? Required, banned, and invariance. Required means it must be present. Banned means it must be absent, and invariance or logical rules that must always hold true. In a refund amount exists, there better be a refund ID alongside it. This layer is still cheap, still programmatic, still fast, but it's catching a fundamentally different class of failures than schema checks. Schema says, is it well formed? Properties say, does it contain what it should and nothing shouldn't? Now let's look at the code, right? The function takes an artifact dictionary and runs 3 categories of check: required entities, customer ID, currency, transaction ID. If any are missing, flag it. Simple. But the real highlight here is the banned pattern block that you see. This is the PII leak, anti-leak check that most teams get. Credit card number patterns, internal host names, and this one's important: prompt leakage. You're helpful. Showing up in the output means your system prompt is leaking into response, and that's not good. That's a security issue. And this simple regex regular expression catches it. Then invariance, at the bottom you see the business logic rules. And this is where the refund amount, but no refund ID. Something structurally wrong with the artifact. These aren't things a schema check would catch, right? And they're not things that you would need a model-graded eval for. They are deterministic, they are cheap, and they're critical. This is the layer most teams either skip entirely or build too late. Don't be that team. Layer 3, model-graded eval. This is where things get interesting, right? Think of this as a certification exam that you would go in. Not naming any vendor here. For the layer defense, the rubric is written down, the scoring is calibrated, and here's a key test. 2 examiners marking same paper should reach the same verdict. If they don't, your rubric isn't steady. This is the first layer that's probabilistic rather than deterministic. It's also significantly more expensive, which is exactly why layers 1 and 2 exist, to make sure you're not only spending model eval dollars on artifacts, they are structurally sound and property compliant. Now, if you ask me, is there any other frameworks exist that you can actually use? Yeah, my honest take in the landscape in 2026, well, there's a lot of frameworks that comes up every day in the IT world, in the age of AI era. There are a number of open source frameworks and commercial products that you can pick one, commit, and ship. The ones that you see, the Phoenix, Arise, the Langfuse, Ragas, Promptfoo, OpenAI Evals, Deep Evals, and everything exists for a reason, right? And if you see Phoenix, they're good at observability plus tracing. And this is something useful if you're already on Arise for production monitoring. And Langfuse, again, open source. If you really want something, the prompt versioning and eval tracking, where you have your own infrastructure, probably this is more relevant for industries like financial services, healthcare. And RAG, this is again a good one if you're having RAG in your AI pipeline. The key strength is RAG primitives out of the box, right? So use alongside, not instead of. And Promptfoo, again, it's open source, light, fast iteration. Early stages, I mean, if you're still figuring out the rubric, this is probably the best bet to start with. And OpenAI Evals, again, if you're an OpenAI shop only, then probably OpenAI Evals will be a lot better. And if it's multimodal, then probably it's less compelling for you. Now, deep eval, PyTest-based LLM evals, and this is something that, based on Python ecosystem, PyTest-based test. If your already team writes, this brings in the best view of using decorator style CI native tests. If you ask me my advice, well, pick one, commit ship. Don't spend 3 months evaluating these tools. Just start based on the strengths that you see and then see where do you stand and then what works for you. Now, imagine you picked one. The key thing is around the rubric that we spoke about, right? So here's what a reproducible rubric actually looks like in YAML. 3 criteria, right? Correctness, completeness, and safety. Each scored 0 to 5. The threshold is 12 out of 15. That's your get. Anything below 12 fails. But the line I really want you to focus on is the inter-rater cap, right? At the bottom, as you see. 0.7 required. What does that mean? It means before you trust this rubric in production, you need to verify the 2 independent evaluators, whether their model or humans, give substantially similar scores on the same artifacts. If your kappa is below 0.7, your rubric is ambiguous. And that means the scores you're getting aren't reflecting artifact quality. They are reflecting evaluator randomness. And that means, again, your whole layer 3 is a noise, not signal. The rubric has to pass its own test before it can test anything else. That's the discipline we're talking about here. And that's very, very critical. Layer 4, human sampling, the last line, but crucially not the only line. Think of this as a code review done properly, not code review where one person rubber stamps everything. Proper structure, calibrated review. This is the most expensive layer in the stack. It's people's time, which is why when first 3 layers exist, by the time the artifact reaches a human reviewer, it's already passed. Schema validation, property checks, model graded eval. The human isn't checking for missing fields or PII leaks. The human is checking for stuff machines can't see. Obviously, if you spot a PII leak, you would flag it, but that's not what you look for. And sometimes it gets overlooked and you don't want to wait for the human check to happen, which is why you need those layers to completely eliminate those structure tests and those PII leaks for you so that you're not overlooking by mistake. Now, 3 principles for making human sampling actually work. First, sample, don't review everything. You're looking at roughly 10% of artifacts that passed all prior layers, plus 100% of the borderline failure from layer 3. Those near misses are where the most interesting quality signals live. Second, look for what programmatic checks can't see. The artifact is technically correct, but semantically off. It's appropriate in isolation, but inappropriate given the broader context. These judgment calls, they are the entire reason why this layer exists, right? Third, rotate your reviewers, different people each week with deliberate overlap of periods of calibration. That's a single point of failure, right? And it's how bias creeps is undetected. If you name these 3 principles, layer 4 becomes a genuine quality signal. If you don't, it becomes an expensive theater show. A quick bonus before we move on, right? And if you want to go deeper on any of this, there is a companion article series on Planet where I'm associated with as a daytime job. It's on the Insights channel. I'll drop the links in the description. You can go and check that. It's a 5-part series that I'm writing. It covers everything we're talking about. You start with beyond deterministic testing and talk about layered failures, taxonomy, and then you can also look at how we can design this evaluation, right? It's completely going deep dive, layer by layer, zooming in, and if this is of your interest, and if you need more, obviously the 4 layers that we covered, it's pretty good enough, giving you a mental model, giving you the framework. And there is a reason why I'm not going deeper here, right? Because I want you to understand the mental model, because the frameworks comes and go, the tools come and go, right? But the mental model, the framework, how do you do certain things that are really, really important. And that's the learning that you can get. And that is what I'm focusing on. And the 4 layers, as we saw, is very key. And then the articles that you see on planet.com/insights, and then I'll drop the links below. You'll actually go deeper on all these. Now, Act 3, going back to our series, wiring it together. So we've got 4 layers. Each one makes sense individually, but the real power isn't any single layer. It's in how they connect. Let's look at the cascade, right? This is the full picture, the cascade. Schema fails fast, properties fail next. Model graded runs on what survives. Human samples what passes. Each layer feeds the next, and each layer saves the next from wasting resources on artifacts that they were already broken. But notice the 2 feedback loops at the top, the drift detection. This monitors all 4 layers over time, or schema failure rates creeping up, or property violation shifting in pattern. It's the model graded eval seeing score distribution change. Drift detection gives you early warning that something in your system is changing before it becomes a production incident. At the bottom, you'll see self-heal log. When the system can automatically fix certain classes of failures, those healed artifacts re-enter the pipeline at layer 3 for re-evaluation. This closes the loop for video 1 that we looked at. Remember when we spoke about the systems that degrade silently? This is it. The drift detection and self-heal are how you stop that from happening. Every layer catches what the previous couldn't. Every layer saves the next from running on something already broken, and that's the design. One more thing that matters: size. The size of your eval set. 20 artifacts, that's a top. It passes when you want it to pass, fails when you want it to fail. It tells you absolutely nothing about the actual quality of your system. 100, that's your minimum for a signal. The smallest set where the result starts to actually mean something statistically. 500, that's where you get real confidence, big enough that drift detection has genuine statistical weight behind it. Big enough that trends are trends, not noise. If you're running eval sets smaller than 100, you're not evaluating, you're helping. Well, this may be coming as an opinionated view, but again, this is based on what I've seen shipping a couple of AI pipelines in production where we have run through different frameworks. I've used Promptfoo, I've used TPeval, I've built my own custom wrappers on top of these. I've built it by old rubrics, have a calibrated view that gets results based on different things. If you're running eval sets smaller than 100, you're not evaluating, you're helping. Well, this may be coming across as an opinionated view, but this is something that I've definitely learned from at least implementing a couple of AI production pipelines. And this is based on my experience. I've used different open source frameworks, as we saw earlier, or Promptfoo, TPeval, and I've built custom wrappers on top of it. And more than enough, I've also built my own evaluation framework for LLM outputs, where you can do an eval on RAG agents, having its own rubric score, a calibrated results against all the LLM outputs that it can come into, confusion metrics, using different metrics in the AI world, like the Rouge, Blue, Meteor, reference-based semantic, cosine similarity. I don't want to throw a lot of jargons at you, but imagine these are some of the metrics that are available in the LLM world. We will get through it, don't worry. This is just to show you that, sometimes these numbers are, important, and the bigger your data set, the bigger your evaluation pipeline is, it's better because you get more confident. Now, what this stops being, right? So we have built a pipeline. We have wired the cascade. Now let's zoom out and talk about what changes philosophically when you adopt this approach. This is the callback from video 1. The passing test is no longer proof of correctness, right? We said that in the first video, and at the time it might have felt uncomfortable, but now you can see why it's true. And more importantly, you can see what it replaces it. Not a single binary password, but a layered defense with a signal at every layer. The question changes. The old question was simple. Did the test pass? The green check or the red X? Ship or don't ship? It was binary. But the new question is not binary anymore. The question is richer and more honest. Did the layer difference have enough signal to know whether the system is okay? That's fundamentally a different question that you're asking. It acknowledges uncertainty. That's what I call in one of the blocks that I mentioned earlier. It's the engineering confidence under uncertainty. That's very, very important. It acknowledges the quality in AI system is probabilistic, not deterministic. And it gives you a framework for answering it with confidence rather than hope. Confidence is a product feature, not a feeling, not a vibe check. Not it seems to work. It's a thing you measure, version, audit, ship, just like a latency, just like uptime, just like any other non-functional metrics or requirements that you come up with. When someone asks how confident are we in the system, you should be able to point to a dashboard with a layer by layer pass rate. Drift trends, eval scores, these are some of the things, and that's what the layer defense gives you, honestly. This gave you a better understanding about what we started with video 1 and video 2 and where video 3 goes. The trilogy closes, right? So in video 1, we mapped the terrain. In video 2, we diagnosed the anti-patterns. And in video 3, this one gave you the architecture and the code to build a layer defense that actually hold up. But the journey doesn't stop here. All the things that we saw, as I mentioned earlier, as a bottom-up approach that we are following, I'm going to go through deep dive. The course opens. Well, I'm not going to give you a traditional training. There are plenty of other partners and friends in the industry already doing that. This is more about helping you understand these concepts in today's world, the kinds of challenges you will face, and what it really means to become AI native. And that's what AI native quality engineering series is all about, right? So what I mean by the course opens again is that this is the beginning of entirely a new playlist. And the first video is about why testers are unusually or uniquely well positioned for AI engineering. And that's where we will start. From there, we will explore a range of topics designed to help you understand how to get started with AI in 2026. Explore a lot of these concepts, starting from prompt engineering to context to RAG, agentic AI, and we will there. And yes, the answer might surprise you. There's lots more coming in the series. Thanks for watching. If you found this useful, subscribe and hit the bell button. The playlist launches soon and we are going deep. Until then, take care and I'll see you next time.